Hey guys, welcome to this video about coordinates and representations. The second video of the series about eigenvalues, from survivor to master of coordinates. So originally I wanted to do one video and put this as chapter 4 of the last video. But it turned out that this topic is way too interesting to rush through it and rather spend some more time in the details. It's also a little more abstract than some other topics, so we're definitely gonna have some fun here. So the perspective of the end of the last video was the following. We diagonalized matrices, we even agreed on that a diagonal matrix is quite capable and very interesting, but we were left like fishes in the end. Such a great diagonal matrix, but excuse me, how does this relate to the original matrix we had? What have we even done? That was the problem, and this is what we're gonna explain in this video. So let's see what the outline gives us here. We'll start with coordinates of a vector and the change of coordinates matrix. This is a thing you probably have heard about, but you were probably also always wondering, how does this really work out? What's the system? Do I just have to memorize a formula? Then we go to chapter 2. From the change of coordinate matrix, we'll transition sort of naturally to the matrix representation of a linear map. This is also the chapter where we'll encounter the highest degree of abstractness in this video. So you could argue in a way it's the most beautiful chapter. I know if I say this, some of you are already getting their buckets to throw up. But you can put them away. It's gonna be fine. And in chapter 3, we are finally closing the loop back to the eigenvalues and stumble upon similar matrices, and then we know what is the connection. Just one more thing about the outline here and the concept. So the approach I'm choosing here is sailing somewhere in between a full abstract overview notation of the whole thing and a more practical coordinate-based, example-based way. So I expect some of you guys, the purists, waving their arms like this, roar, shouting, well, this could be done far more general and whatever. And I expect the other guys be more like, roar, what is this abstract notation? I want more examples. Roar. So what can we do? Well, let's do it together. Okay. Some knowledge is a prerequisite as always. So you should be familiar with linear combination Gauss algorithm, probably eigenvalue video, and of course the basic linear algebra notions. But in a way, you need less prerequisites for this video than the other one. Kind of interesting. So, anything else? Do you want to say anything? No? All right. Then, can you please close the door? Thank you. Let's start. I have a line here this time because I want to keep like the general equations to the left and some examples to these equations to the right. What do we start with? Let us start with a coordinate vector of x with respect to the standard basis En. Okay, just write it down. The coordinate vector of the abstract vector x and let me introduce to you our special guest tonight. Again, the vector x. Very nice. Isn't it a great one? Now, what do we mean by coordinate vector of x with respect to the standard basis? Well, It's actually a column of the scalars of the linear combination by En. Looking like this. So we usually write this x equaling x1, x2, xn. So on the right side, you have the coordinates of x, but in this notation, there's nothing about a standard basis or any basis. And this is in itself rather unprecise, because we actually do not understand what this is supposed to mean if we don't expect a standard basis. So if we write this out, this would be like first scalar times the first basis vector. So this is the linear combination of x. And so on, you know the drill, until the last one. Or a little shorter, x1, e1, so far so good. That's what you probably have seen many times. But it's actually a little more subtle here, because over here in the linear combination, we specified the standard basis. Meaning, I'm going to do this in blue because it's our choice, which we did. We have the first standard basis vector over here, second one over here. So this is an example in R2, obviously. And by that, we also give a coordinate system, the Cartesian coordinates as we know them. And although this is not drawn really precise, what I mean is the vector 1, 2. But if we write 1, 2, 1 times e1 plus 2 times e2, we actually expressed x in its coordinates with respect to the basis e. Oh, I put en up there. Let me quickly remove this. I just want e. So here I introduced square brackets, really meaning the coordinates of x with respect to the basis e. And this is what I should do here as well. And in a way, I should even do it over here. Always saying, if you're giving coordinates, you need to specify the basis you're working on. Otherwise, this could be anything. Now, obviously, usually you're talking about the standard basis, as we're doing here. And in that case, it's almost always left out, this index. But since we're talking about exactly that topic, let's carry these indices at least for a while. So this is our first E coordinate system. And I put the vector x in white to argue that this one is fixed, but the coordinates 1, 2, they depend on the basis we chose, and this is why it's blue. Okay, let's breathe for a moment. So here you have this sort of new notation, which sounds a little or looks a little awkward, probably, but really it means, okay, you are giving me coordinates, but then tell me also which basis. Now, some of you might be like, okay, very good, but what about these 1000 notation on the right side? Aren't these coordinates as well? And if so, what basis do we have to specify there? And in fact, this is a very good remark. These ones are coordinate vectors. They refer to their own basis, meaning this first coordinate here, the 1, is saying take 1 times the first basis vector plus 0 times the rest. And the first basis vector is just the 1, 0. So that's fine. You could, this is a side note, you could say let's have a basis vector vi with respect to the basis v, so the ith basis vector of the basis v. And how does this look like? Well, it looks exactly like zeros and a 1 at the ith position. Like the standard vector we know. V is base. So far, nothing new. We just specified which basis we are working on. And now we specified this. Obviously, there must be the possibility to have different bases. What about the coordinates? What about the coordinates of x with respect to the basis b? A different one. Well, then you would probably, in analogy to the lines above, write x index b, so the coordinates of x with respect to the basis b. Then you would have some sort of coordinates here. Let me call them lambda. And you might want to note that you're talking about b. Let me make a remark here. If you see any coordinates in this video, or actually in general, and no basis is specified, then you know that it has to be the standard basis you're talking about. Otherwise, it doesn't make sense. So if I leave the indices out here, I also mean the standard base, or I made a mistake and you probably have to find it out. So sorry. Good. Now you might ask, well, or we should ask, how do we get these different coordinates of x with respect to a different basis? This would be the question. How to get the b coordinates of x when b itself is given in e coordinates? Now, this sounds more complicated as it is. What I mean by that is, let's introduce b, the second coordinate system. We still have the vector x. You see it's untouched. But now let me choose this coordinate system. And the full blue arrows are the new basis vectors, b1, b2. This is a different basis of R2. So that's fine for that. It doesn't even have to be orthogonal, but we just do it here for simplicity. And the new b basis, let me give it, for example, as the vectors 1, 1, and 1, minus 1. These are the vectors over here. And this is what I mean by the basis b is given in e coordinates. This is something we usually take for granted, or we probably don't think so much about it. But this b vector here has coordinates expressing its linear combination over the basis e. As you can see here, 1 to the right, 1 up, 1 to the right, 1 down for b2. But now, what are the coordinates of the vector x with respect to the basis b? So you would look how much of each axis you have to take to reach this vector. And then you do something like lambda 1 times the first basis vector plus lambda 2 times the second one equals 1, 2, equaling x in e coordinates. That's the general equation you do. So what would lambda be? Lambda 1 and 2. There's going to be solid formulas for this, but we can do this right now just like this. So I suggest 3/2 times 1, 1 plus minus a half times 1 minus 1. And I hope you agree that this is 1, 2. And that's exactly the thing we're looking for. So what we found is the vector x in b coordinates, like up here, those lambdas would be 3/2 minus 1/2. Lambda 1 and lambda 2. So far so good. So we left the vector as it is, but we chose different bases, therefore a different coordinate system. We found different coordinates, lambda 1 and 2, which express this vector x with respect to the basis b. So let's do this for Rn on the right. So we had the vector x, and we had it with respect to the e basis, standard x. Now, like in the example, we do the linear combination. Lambda 1 times b1 plus lambda 2 times b2 until the end. Really, the vectors b we got, or we defined over here, were with regular coordinates just like this one, the x. So to be really precise, we should write b1 with the index referring to the basis itself refers to. Now this is like an equation we can solve. We did this in the easy example over here. We found the lambdas, and the lambdas written in a column giving us the coordinates of x with respect to b, which was the question we're just looking at. But what can we do from this expression if we do not just do it in our head like on the right side? The trick we're using is writing this equation with a matrix. Just by like optical surgery, we can do this. I write it down for you, and then we can see if we agree on that. So let's just do equals. Now we make a matrix. We take the basis vector b1, write it in a column, and all other basis vectors b until bn. And we collect all the scalars lambda, putting them behind. Now reassure yourself that this is actually correct, that this is the same. But you probably can do it like this. Look at the first line times column, then you would always get b1 lambda 1 plus b2 lambda 2 and so on. And you would get this for all lines. So this is fine. All right. But what do we have here? Let's look at this more in detail. So if we give this matrix a name, let's call it M. Then we have M times, and I'm leaving space here on purpose, times the vector x with respect to b. Shocking news. This one is actually this one above. So here we already collected the scalars, the coordinates of x with respect to b. So we could actually note a small b here if we want to. But let's also give the matrix M some more indices, right? Otherwise it doesn't look cool. So what indices do we give it? Well, I suggest the following. And there's many different notations in the literature, and most of them are confusing, and this one is also, but maybe not that much. So I suggest put in the basis, or the basis of the space where we started. Starting means which vector we multiply the matrix on. And this vector, as you see here, comes from B. And then comma, the basis of the space where we're going to, meaning the result we get. And the result over here are E coordinates. All right. So you put in B vectors, you get out E vectors. And what you should note, this matrix M with some indices has n vectors, each of them having n coordinates. So the whole thing lives happily forever in its space of n times n matrices over a field like R. So what we did up to now, we just wrote the linear combination of x, put in a new basis b, and then rewrote the whole thing as a matrix. Because why? Because now we can solve for the lambdas if we have a given x. So for a given x in standard coordinates, compute the lambdas via Gauss algorithm. How does this look like? Well, let's give this an xe, just that we see it over here. How does this look like? How do you solve this system of equations via Gauss? Well, you take this matrix until Bn, and then you extend it with the solution vector. I mean, from this equation, the xe on the left. So this would be x1, until xn. These are column vectors, so they also have n elements. Well, let's do this for our example, I would say. We already got the lambdas by just looking at it, but let's confirm that we're right. So we had the xe was 1, 2, and now we build m by writing the new basis vectors just in columns. They were 1, 1, and 1, minus 1. Oops. Well, all right. Lambda 1, lambda 2. And this one is MBE. And now, as I said, we can go for the matrix 1, 1, minus 1, extended by x. This is 1, 2. And now solve via Gauss, giving us, for example, 1, 1, 1, 0, minus 2, 1. And from that we get lambda 2 equaling minus 2 times lambda 2 equals 1, so equals minus a half. And combine it with the first line and you get lambda 1 equaling 3 halves. So you're right. And also we get, as before, the coordinates of x, hard to pronounce, with respect to b being that. Very nice. So if you want to have the coordinates of a vector x in a new basis coming from the standard basis, you can do this. But maybe you want to have something more powerful. This is not enough. You do not want to solve this for every vector x via Gauss. Maybe you want to have a map, meaning a matrix, which you can multiply on x so that you get the new coordinates right away. That would be much easier, right? And this is actually already implemented in the equations we wrote down. Just write down the line before. How do we do that? Well, let's repeat the same equation we had there all the time. So instead of writing the matrix with the B columns, I'm just using the name MBE. And the vector we put in the B coordinates. So this is actually the other way around. Here you put in B coordinates and you get E coordinates, which is pretty good, but we want to give E coordinates and get B coordinates. Well, now, this is why I said you need inverse matrices in the beginning, or noted it down in useful knowledge, because now you can do the following. You take the inverse matrix, which goes from E to B, and multiply it from the left. Let's do that first. So you get MEB inverse times x. You can also use a regular times sign. And now you have the inverse and the regular one. And you know what that yields if you know inverse matrices. First the vector x with respect to b. This one gives us the unit matrix. So this is basically, let's call it In times xb with In unit matrix. So all in all, we have the B coordinates equaling the matrix from E to B, which was the inverse of M times E coordinates. That's it. That's what we are asking for. Now, some of you are like, I have heard something about that not all matrices are invertible, and shouldn't we check that this is the case? Absolutely. But this matrix M is invertible by construction, so to say, because matrices built of linear independent vectors n in the Rn, they are invertible always. You can show that. So actually this M lives in the group of invertible matrices. So no worries about that. M is invertible. Just as a side note. Let's try in our example if this works as well. So we had M, and that was 1, 1, 1, minus 1. Now what is the inverse of M? There's different ways to calculate that, and you probably practiced some of them if you wanted it or not. But for 2 times 2 matrices, there is a certain rule which makes it easier. And it goes like that. If this was A, B, C, D, then you have 1 times the determinant of M, which is AD minus BC, times changing the diagonal elements and multiplying the other ones by minus 1. So in this case, this is 1 times minus 1 minus 1 is minus a half times changing minus sign. That's that. So we found the inverse matrix of this formula down here. Let's apply it to the vector 1, 2 and see if we get the lambdas which we calculated earlier, which were these ones. All right. M times x respect to the e basis equaling minus a half, minus 1, minus 1, minus 1, 1. And that's minus a half. If we do this before, then we get minus 3, 1. That's in fact what we were looking for, 3 halves minus a half. Very good. So in fact, what we found out kind of works. And this already leads to a sum up of chapter 1. Because we found 2 matrices which transform our coordinates from one basis to coordinates in a different basis, but let the vector as it is. So obviously these matrices can be called change of coordinates matrices. So the change so if we want to have E coordinates, we take MBE. This is only a summary of the things we already had. And if we want to have B coordinates, we take the inverse. And we put in the other coordinates. And most importantly, MBE was very easy to construct. It was just the B basis vectors, expressed in regular coordinates, of course, in columns. So really nothing to do. That was already chapter 1. We explained what coordinates are, and we explained them by the linear combination and the scalars in front of that. And then we changed our bases, or let's say we changed our coordinates of a certain vector x. By doing so, we found that there are matrices for that which do this, and they are called change of coordinate matrices, and they are constructed really easily. In 2, we're transitioning from that matrix to the general matrix representation of a linear map. Let's write that down first. So I want to introduce the matrix representation of a linear map in a way where we first look at the change of coordinate matrices in a slightly different way, asking, what did we really do there? We actually applied a matrix on X, that is a map on X, but X stayed the same. So, but we still changed the coordinates. What did we really do? We didn't change X, only coordinates. And that is actually equal to applying the identity map on a vector. The identity map is the map where you do nothing, where you do not change the original element. So we could argue that this was the same as applying the identity map. But we didn't just apply it, we applied it with respect to different bases, because after all, we changed bases and therefore coordinates of the vector with respect to different bases. Let me draw a sketch. Let me just put this over here. Let's just redraw what we just did before. We had the standard coordinates, standard bases, and therefore standard coordinates. And we also had these coordinates. The associated rotated coordinate system. And in the orange one, these were the 2 coordinates with respect to the orange bases. And in the blue one, these were the coordinates. And now, what do I mean by we applied the identity map? Well, the identity map applying means ID for identity map of X equals X. So this vector sort of gets mapped to itself. It doesn't change. So what we did is we put in a vector of Rn, we get one of Rn. We do nothing with the vector, but we are more precise. We put in the vector in E notation, E coordinates. What we get is the vector coordinates with respect to B. And now how do we get this together? Well, therefore, you have to know that every linear map can be expressed as a matrix, and this matrix depends on the bases. the linear map identity can also be expressed as a matrix, and this one also depends on the basis. So we had X, for example, in the E basis, and the matrix MBE now gets a little more notation, why not? Was the representation matrix for the linear map identity, which would be the linear map T, in this case the identity, times the B coordinates. So as writing a vector with coordinates but not referring to which basis you mean wasn't precise, the same is true for matrices. Matrices represent linear maps, but they are not unique in the sense of the linear map can be represented differently and must be represented differently regarding different bases. So if we build this MBE, or if we just repeat how it was built like that. Now again, with the correct coordinate reference. If you remember, in the columns, the new basis vectors. But to be more precise, if we represent the identity, then there's something different here as well. There's actually the identity of B1, so the mapped vector by the map identity, doing nothing, of course. But in coordinates of the new basis, you started in B and you go to E and you express these coordinates in the new basis. And you do this for all basis vectors. So this part here was sort of meant to transition or motivate how all matrix representations of linear maps are built by definition. This was to show that we already did this, but as we skipped all the notation, we didn't really see it. But we already found out that the change of coordinate matrix is the matrix representing the identity map and respecting the basis to come from and to go to. So this is now the big thing. In fact, any matrix representation of a linear map T is built like that. Let's get some more space. A bit like that. What do I mean by that? Well, we have a matrix representing the linear map T. We have a basis in the pre-image space and one in the image space. We go from A and get something in B coordinates. And this, per definition, is doing the same as before, but now with the general map T instead of ID. Take the basis element of the starting basis, capital A, small a1, map it with your linear map, then express the whole thing in coordinates of the new basis, B. And do this for all basis vectors in the starting basis, capital A. So in the end you will get T of AN. Last basis vector mapped with the map expressed in new coordinates, and all of these vectors written in columns. We should say that T can go from Rn to Rm, so it doesn't even have to be the same dimension. And let me write this in text one more time. Map basis vectors of A with T and write result as linear combination of basis B, and that in matrix columns. Okay, that's a lot of text, just describing what's written down here, but sometimes text is easier, so why not? And now there's also another formula or equation which does exactly the same, but is written a little differently. This other form goes something like this. Map your J's basis vector with your linear map T and express it as linear combination of the new basis B. So this sum in the scalars in the B, that's the linear combination. And these scalars are actually the elements of the matrix M. This is MAB of T. So this is totally equivalent in the sense of you can find your matrix element by this, or this is the same. So let's give it a nice red box. This is sort of the heart of this whole thing. And if you want to, because it looks so hard, give it some flames. So this is the point where I said in the beginning, you might be, or it's a little to the abstract side in the sense of notation, which always is a little harder to intuitively understand, but also if you do understand it, gives you the better overview. Let's do an example here. We take a map T, which goes from R2 to R2 for simplicity reasons. As I said, it can be different. We also define how T is acting on a vector expressed in standard coordinates, because we have no choice. If we want to express T somehow, we need to pick a basis already. Having said that, let's take two different bases of R2. For example, the basis A being O minus 1. It's all in standard coordinates right now, so I'm not even going to note the E's all the time. This is the one we already know from the earlier examples. Maybe we can draw our new bases here real quick. We get something like this for A1, A2. This is this is A1, A2. And for that one, we get this and this. Now we want to find the representation matrix of this map T regarding starting basis A and finish basis B, so to say. So we are looking for MAB representing T equals question mark. Now we really strictly follow the scheme in the red box. Map A1, you get 2 times x2 is minus 2, minus 1 times x1 is 0. And now you express this vector in coordinates of the new basis B. How do we do that? Well, we had it before. We take the vectors of B and per Gauss, this is what we want to get out. And this will give us lambda 1, lambda 2, or x1, x2, give us the coordinates of the image of A1 under T with respect to the basis B, which is in the columns here. So this is 1, 1, minus 2, O minus 2, minus 2, plus 2, very important, leading to, let's call it x1 and x2 equals minus 1, and x1 equals minus 1 as well, because minus 1 is minus 2. Very nice. Then we do the same thing for the second basis vector, which is 4, 1. So this is really just doing the same thing again. That's why I'm speeding up a little bit. And you can take your time if you want to. Always suggested, of course. And then I get x1 equaling this, x2 equaling this. So what did I do in the red box? I did exactly calculate each of these vectors, mapping the old basis vector, expressing it in new coordinates. Or here, mapping the old basis vector A1 and 2 with T, expressing it with coordinates respecting the basis B. And I used the technique of chapter 1. So together, or from that follows that MAB of T is just these guys in columns. That was the first one. That was the second one. It's easier as you saw, probably. But maybe we're wrong, so let's test it real quick. Let's go for MAB of T times, and now we pick a vector, but pay attention, the vector which we put into this map, or which we multiply here, which is the same, has to be in A coordinates. I took A1 just for fun, but I pay attention to express it in A coordinates. So that would be minus 1, 5 halves, 3 halves. What is the vector A1 expressed in its own coordinates? We had it in the very beginning of the point 1 in this chapter. And we said, well, in its own coordinates, it's just 1, 0. Because A1 equaling 1 times A1 plus 0 times A2. And that's giving us minus 1, minus 1. And as you see, once we applied the matrix, we get B coordinates. So this really are the B coordinates of the mapped A1. So you could say this are the B coordinates. So that's all we wanted. We wanted to have a map where you put in A coordinates and you get out B coordinates of the image. Now, just to show that this is supposed to be correct, we can go back to the standard basis, which was minus 1 times first basis vector. B1 was 1, 1, minus 1 times 1 minus 1 is b1, b2 equaling minus 1 is minus 2, minus 1 plus 1 is 0. And that's exactly what the image of A up here in E coordinates was like. So that all worked out quite nicely. There's a certain chance that you are still confused with all these coordinates, and I guess you should be, but I hope you find your way through this. The good news is you can really just follow the scheme in the red box. And the even better news is that now having this method of explaining the same linear map with respect to different bases, we can finally come back to the eigenvalue problem where we started from in the other video and see how the diagonal matrix is related to the original matrix. So let's do that. Eigenvalue context. Similar matrices. What was the eigenvalues stuff again? We said in the beginning of the survival recipe that you usually get a matrix M, and what we usually don't think about, but what we get there is probably the matrix M with respect to the standard basis, representing a linear map T, which is also not specified any more than just this. But it's enough, of course. So that was the start of video 1. And then we said, well, this matrix M E is usually not very nice, especially not diagonal. And we check if it's diagonal. So for our context, let's say let M be ugly, that is not diagonal. But let it also be diagonalizable. That's what we, let's say we found that out. Diagable. So there is something like a diagonal matrix, M diag, with the eigenvalues on the diagonal. Especially about diagonal matrices and so on, we talked in chapter 3, and this was also chapter 2. So same video 1. Now, let's make a statement. We are saying, and this is the answer to the so often posed question here, M diag is the representation of the same linear map as MEE was, the starting matrix, but with respect to different bases. So let's write that down real quick. So M diag is not just anything, but it's really a matrix M acting between the eigenvector basis B and itself, representing the same T as MEE up here. So what should we do here? Well, if the diagonal matrix is acting on vectors with B coordinates, let us transform all coordinates of all vectors to the B basis. And we know how this works. We know that we can have a matrix which we multiply on the vector x and E coordinates, and we will get the B coordinates of it. That was a change of coordinate matrix from the beginning. Yeah, so let's do the change. We know that there's a matrix where you put in, for example, standard coordinates. It represents the identity. This is the change of coordinate matrix. And you multiply it by x with the old e coordinates. And then you get the xb coordinates. These ones we can put into MBB. Once we transform the coordinates into a system which fits to the diagonal matrix, we can apply this one. So now and only now we can apply the diagonal matrix. Applying means multiplying. So we go for the diagonal matrix times the change of coordinate matrix, which transformed each vector into the form fitting into this one, the diagonal matrix. And we can also write, since we calculated the first row before, we can go for MBB representing t times x in b coordinates. So this one are the coordinates we want to put into the diagonal matrix. Which had the eigenvalues on its diagonal. Maybe an example from video 1. Where we had the ugly, in quotation marks, matrix 0110. We also calculated the diagonal matrix to be 100 minus 1. In that video, we didn't specify any bases down here because this was reserved for now. And we had the eigenvectors one, one, and 1 minus 1, which is also the basis we were using in this video before. Now, if this is the new basis, the old basis is the standard basis, then we can right away define MEB ID to be, that's what we know already, the inverse of this matrix. And this one, B to E, was just writing the new vectors, new basis vectors in columns. According to chapter 2, the red box, mapping the old basis vectors and explaining in new coordinates. And this one, the inverse of that. So we inverted this matrix before, it was -1/2 times -1, -1, -1, 1. Okay, so we found the change of coordinate matrix, where you put in standard coordinates and you get b coordinates, so that you can put those guys in front of this diagonal matrix. Well, let's apply the diagonal matrix, which we already found here, or let's say defined in this video, to MEB -1/2. And what do we get? equally. We get a +1 on the bottom left, a -1 on the bottom right. We keep -0.5. MBB times MEB. Now, we transformed all vectors so that we have it in B coordinates and can put it into the so great diagonal matrix. Now you say, well, but actually I don't want to have anything to do with these eigenvector basis coordinates. After all, standard basis is always the best. So why not change coordinates back to the original state once we applied our map? Then once we applied our map. So let's write this down. You don't want anything to do with the B basis. Let's change the coordinates back. Well, what do we do there? I give you that minute. Well, we put another matrix in front. This one, the matrix which transforms our coordinates from B coordinates back to E coordinates, but doing nothing with the vector identity matrix, change of coordinate matrix, and multiply the rest. MBB, this was the actual map T. Then we had the forward transformation in the beginning, but actually doing nothing on the vector. And we applied it to a vector in standard coordinates. And this whole thing is just the same as saying I did my MEE, the ugly matrix, times standard coordinates. So that was the map, the actual map. This was chord change 1, code change there and back again. This line is really a very interesting line where you have your map T, which you really want to do, expressed in E coordinates, and you're saying, well, I can also go from change my coordinates, then use a matrix which looks better to me, a diagonal matrix, and then go back. Obviously, this is not possible for every matrix, but in case of our diagonalizable matrices, it's definitely possible. Let's just see if this all worked out as we wanted it to do. So we had MBB times MEB, so there's missing MBE, which is, we had it here, 1, 1, 1 minus 1, MBE. Now I multiply it with the other two. This is -1, -1, +1, -1, minus a half. And let's see what happens. We get 0. Let's go on a new line. For example, -1, +1 is 0. The rest is this, times minus a half, giving us 0, 1, 1, 0, which was, as hoped, mee of t. So that worked out nicely. And from here, you can say this a little more generally, or in a more general fashion, that actually every two matrices where you can find those invertible square matrices of coordinate change, so that this whole equation holds, are called similar. With the change of coordinate matrices S and S minus 1. Yeah, having found that, we can say that a diagonal matrix here in the middle is similar to the original matrix in the sense of the definition of similar here. Very nice underlining, I know. Before I conclude, I want to do some more next level drawing or sketching, which hopefully explains a little better how the same linear map T is acting, but it has different matrices. I'm going to draw two sketches. One has a coordinate system with the basis of eigenvectors, and the other one will be the standard coordinate system. And of course, the standard bases are not eigenvectors in this example. So let's start with the eigenvector basis B. Let's say this looks like that, where this is B1 and this is B2. This is not to be seen in a 3D tilted way, but this is really R2, but a non-orthogonal basis. But it's a vector, a basis of eigenvectors, because now I know that, let's say, the map T applied on this basis vector is just stretching it by 2, whereas it's stretching the other one by -1. This is T of B1, T of B2. You see how they are not changed in direction, but only stretched. This was good as explained in chapter 3 before, because now you can map every vector pretty fast. For example, let's take this vector. Let's see how this mapped. Well, it has a component here and a component here in the eigenvalue basis. This component gets stretched to the 2, and this one gets a switched sign. So in fact, you're reaching this point. As I said, next level drawing. And the matrix M representing this map T in the basis B of eigenvectors. You could write this down, just so. What is it? It's 2, 0, 0, minus 1. The eigenvalues on the diagonal working like this. Now what happens if you take the standard basis or the original basis? For this particular map T. First of all, let's draw the coordinate system. And let's draw E1. Now, this one wasn't a coincidence. It's supposed to look like E1. Now, we already know what happens to E1 if you map it. It goes somewhere over here. T of E1. You see how the linear map T is doing the same thing to the vectors, but here it didn't stretch the basis vector, whereas here it did change the basis vector, this one. Therefore, while we could decide for every vector in the eigenvector basis pretty easily where it's gonna go, here it's not that possible, not that easy, because the matrix cannot be diagonal here. Because if it was, it would only stretch E1. But E1 isn't just stretched, it also has a y component. So that cannot be diagonal. I want to keep this quite short, so I will do one more example, which we also had in the chapter 3 before, for the taking the power of a diagonal matrix. Taking the power of a matrix. So let's say you have this ugly non-diagonal matrix respecting the standard basis. And now you actually want to take the power of 100. Now, as you know, this one is similar to the diag matrix with respect to the eigenvector basis. And we had these S and S minus 1, or M, but I just take S to make it a little shorter. And we take the 100. This is from the equation of similar matrices. Now let's do the right side. This is S, M, S minus 1 times S, M, S minus 1, and so on, equaling, you can leave out the brackets, S, M, S minus 1, S, M, S minus 1. And now there's a pattern in here, which we can use. Sm stays the same, but this one is the unit matrix. And here comes again a unit matrix. And this is nothing else than multiplying by the neutral element, and you can leave that out and you get m to 100 of s minus 1 times s minus 1. And this, since the m on the right side here is a diagonal matrix, can be calculated really quickly, whereas this one is more like the forced labor camp of mathematics. With that, I thank you very much for listening. I hope you had some insights into the topic of coordinates and representations. I will take a minute to sum it up one more time. but I wanted to say thank you before. So with that, let me quickly sum up the series of Eigenvalue from survivor to master of coordinates. In video 1, we started with the Eigenvalue survival recipe, which was consisting of 3 steps, and that's what everybody knows, hopefully. Then we tried to understand this recipe by looking at the eigenvalue equation and the geometrical meaning. We also agreed in chapter 3 that diagonal matrices can be quite good. And then we went to this video. Even if you didn't watch the first one, this one is possible as a standalone. And we started from explaining coordinates of a vector and also looking at the way how we can change them, finding the change of coordinate matrices. Then in the next chapter, or subchapter, we found that these matrices actually are the representation of the identity map with respect to different bases, and that every other matrix representation of a linear map T is built in the same pattern. And we noted that pattern down, found an example. Finally, we made our loop back to the eigenvalues, showing that the diagonal matrix is actually similar to the original matrix, and there's 2 change of coordinate matrices in front and the inverse in the back is enough to show that they are equal if you do that. So that was answering our question, what does the diagonal matrix have to do with the original matrix? I hope you're all confused and you hate this video. And if you do so, oh, wait a minute. Anyway, please don't like, don't subscribe. Anyway, see you next time.